ChaosBook, like every other textbook, is a book in reverse. You work, and then understand something. And then to explain it, you have to work backwards. So when I discussed symmetries a long time ago, it might have seemed contrived. Why should you care about symmetries, relative periodic orbits? And by the end of the game, we learn how to compute spectra of evolution operators, and that's all we need to know about chaos. That gives us all predictions for a long time. But one of the technical details is that you have to know how to compute spectra when there are symmetries. Here is a bifurcation between kinds of people that should learn nonlinear dynamics. I hope it's still true that physicists learn quantum mechanics, even though a large fraction of this building doesn't use H-bar in any shape or form, but we still train students quantum mechanics. It's held for people who have a background in applied mathematics or engineering because they've learned their linear algebra, so they know something about groups, but most of them have not learned any quantum mechanics. So what happens now might seem mysterious to them. It's much easier for people who have quantum mechanics background. From now on, I know everybody's going to suffer, but I guarantee you I'll suffer more than you, because trying to explain these things to innocent minds is hell. I will do it in 2 steps. The first one, I think most people can understand fairly easily, and that's what happens when you have discrete symmetries. How you think about computing spectra of evolution operators in presence of discrete symmetries. The simplest case is very simple. When you have a discrete symmetry, for example, you have a one-dimensional function on a line, and your law of evolution, your Hamiltonian in quantum mechanics, is symmetric under flipping that line. You have probably learned at some point that if you write any function as a sum of symmetric and antisymmetric part, that evolution doesn't mix them. You have a selection rule. So there's a world of functions which are in symmetric subspace, world of function in antisymmetric subspace. First time we learned it in physics was in trying to understand ground state of helium. There was auto and para helium experimentally, and they didn't understand why they seemed to be very stable, very different ground states of helium. In presence of exact symmetry, these spaces are not connected. So then we'll generalize that. And that's an example of discrete one. So I'll work out how it works for one-dimensional maps. And I've already snuck it under the radar last week, because when I taught how you think about diffusion, I actually taught you how to quotient the translational symmetry when it's discrete.